So we're going to look at segments within circles, much like when we looked at angles within circles. There's a lot of relationships going on. Depending on the types of the segments, slightly different formulas. So if you have two chords that intersect inside a circle, then the products of their lengths are equal. So that means you take AE times EB. I'm going to change the letters around a little bit. Each chord is cut into two lengths, AB and XY. And the formula is just A times B equals X times Y. So if you multiply both parts of one chord together, and you multiply both parts of the other chord, the answer is going to be equal. You just have to remember that you're sticking within one chord. You don't jump from line to line, you just stick within one chord. So, looking at this example, we have the 6 and the 2 are from one chord, so you multiply those together. And then the other chord has the X and the 3. Multiply those together. And then solve it. So 3x equals 12, so x equals 4. That's it. The two parts of one chord multiply together to equal the two parts of the other chord. Same thing going on with this equation, or this circle. The two parts of one chord, x times 6, equals the two parts of the other chord, 9 times 8, which is 72. So x equals 12. And for our last one, you can see that they don't give us the other length here, but they do tell us that AD equals 12. So that entire chord has a length of 12. So if this side is 3, that means the other side is 9, because it has to add to equal 12. Then we can do 3 times 9, 27, equals x times 14. Divide, it doesn't work out perfectly, but you get 27 over 14, a little bit less than 2. But just leave it as a fraction. If you wanted the decimal, if you needed the decimal, just type it into your calculator and get it. So there's a special relationship with a chord and a radius. And if you just extend the radius all the way across, it becomes a diameter. That's why I said a radius or diameter. Usually you'll just see it as a radius then. So a radius is perpendicular to the chord if and only if the radius bisects the chord. Remember that if and only if means it's true either way. If you know one of those pieces of information, the other piece is also true. So if it's perpendicular, then it bisects, and if it bisects, then it's also perpendicular. So here we have that they are perpendicular. You can see the little right angle down there. And they form it into a triangle. Now, since that's a triangle, it's not actually a new formula, it's Pythagorean theorem. We've got a right triangle. So a squared plus b squared equals c squared. If you remember the Pythagorean triples from the last framework, This would be a lot easier because every single one of these is a Pythagorean triple. This is a 5, 12, 13. This is a 3, 4, 5. And this is a 8, 15, 17. If you didn't remember that, if you didn't recognize those, you just have to do Pythagorean theorem and get 13 squared equals 5 squared plus x squared. You would solve for x and you would get 12. Same thing here. You would do 25 squared equals 4 squared plus x squared. Solve and you would get 3. 17 squared equals 8 squared plus x squared. Solve and you get 15. So the question that you're going to see with these, though, is not going to say find the length of that side. It's going to say find the length of the chord. So remember we said that if it's perpendicular, it's also a bisector. So if the left side is 12, so is the right side, which means the chord is 24. If the left side is 3, so is the right side, so the chord is 6. If the left side is 15, then the right side is 15, so the entire chord is 30. So in addition to chords, we have secants. Secants are like chords, but they keep going to the outside of the circle. They go through the circle and keep going. And the formula for secants is you take the entire length of the secant segment from A to E, the whole length, times BE, which is just the outside part. Take the whole length of the secant times the outside part. That's true also for the other side. You take the whole length, C to E, times the outside part, DE. The whole length times the outside part for a secant. So we'll look at some examples here. These are secants. So we're going to take the whole length of the secant times the outside portion. So let's start with this one. You take the whole length all the way, that'll be 12, times just the outside portion, which is 6. That will be equal to the whole length of the other secant. You have to add 5 plus x times just the outside piece, which is 5. So we have our equation. We just have to solve. So we're going to distribute. That's 25 plus 5x equals 6 times 12 is 72. So we're going to solve for x. So we subtract the 75. You get 47. And divide, you get x equals 47 divided by 5. You could get the decimal for that if you wanted to. Be 9.4. Or you could leave it as a fraction. We'll do the same thing for this because we have secants. So you take the whole length, 8 plus 6 is 14, times the outside piece, 6, equals the whole length, x plus 7, times just the outside piece, which is 7. And then you distribute and solve. So subtract the 49. So you get 5. Same thing for these two. Secant, so you take the whole length times the outside. So that whole length is 10.4 times just the outside, which is 5, equals the whole length, x plus 4, times just the outside, which is 4. So 10.4 times 5 is 52. Distribute, you get 4x plus 16. Subtract the 16, you get 36. And divide. You get x equals 9. Same idea for this one. You take the whole length, 4 plus 6 is 10, times the outside piece, which is 6, equals the whole length, x plus 5, times just the outside, which is 5. So 60 equals 10x plus 10. So x equals 5. That's not a 10. That should be 25. So we get 35. And then x equals 3.5. So we've got a secant and a tangent now. The formula for the secant segment is the same thing. You still have the whole length times the outside. For a tangent, there's only one segment. There's only the outside segment. Tangents don't go inside the circle. So that's why it's squared. The whole length is the outside. So for tangents, you just square whatever the tangent segment is. Secants, you do the same thing we were just doing. The outside times the whole length. So we're given the diameter of the Earth is 8,000 miles. And a satellite is orbiting 6,400 miles above the Earth. So this segment is 6,400 miles. its range is shown by SP. Set up an equation according to that theorem, the secant tangent theorem, and solve for x, solve for its range. So for tangent segments, we said it's just squared, so x squared equals, this is a secant, so we do the outside length, the 6,400, times the whole length, 14,400. So you multiply, you get a really large number. Four zeros. And then we're taking the square root of that answer to get x by itself. So after you do the square root, it's 9,600 miles. Do the same thing for this. We have another secant and a tangent, so you take the tangent side squared equals the secant. For the secant, you do the whole length, 2 plus x, times the outside piece, which is 2. Distribute, you get 4 plus 2x. Subtract the 4, you have 21 equals 2x. So x equals 21 over 2, or 10.5. On a bird watching trip, you travel along a path tangent to a circular pond, so here's our path, to a lookout station that faces a hawk's nest. Given the measurements in the diagram, how far is the nest from the lookout station? So this is our tangent segment right here. From where it touches the circle to the lookout station is 100 yards. That's the tangent segment. You square the tangent segment. And we have the outside portion here is 25 yards times the whole length for that secant. So you don't have to do any addition because they tell us the whole length is x. So 25 is the outside times the whole length is x. So you square the 100, you get 10,000 equals 25x, and then divide by 25. X equals 400, and our units here were yards. Our last little theorem, if you have two tangents, they are congruent. They have the same length. So if we talk about what we were just doing, we said with tangents, it's always whatever the tangent segment is squared. So this would be, if these were A and B, you would have A squared equals B squared. So it makes sense that they have to be equal. The squareds don't really matter in this case. So two tangent segments will always be equal. So we can get a little more complicated than that because just having two answers always be the same is a little bit too easy. We're going to look at a triangle that goes around a circle. So the circle is inscribed in the triangle. Now, these are all tangent segments. So since this side is 14, so is that, because tangent segments are always equal. Since this side is 11.2, so is the other tangent segment, 11.2. And the 10.8, this will also be 10.8. So the question says to find the perimeter. So you add all of those up and you get the perimeter is 72. You add up all 6 of those numbers. So for number 2 over here, 12.8, so this is also 12.8. This side's 13, so this is also 13. Then we have the whole length is 23, so we have to do a little subtraction to figure out what's left for this other side. That's pretty easy though, 23 minus 13 is 10. So then the other tangent segment is also 10. So to find the perimeter, you add all that up. You get 71.6.